In this video, we're going to do a review on some basic principles of matter. So when we first deal with matter, we want to think of what is matter. And kind of the most basic definition you can think of is anything that takes up space and has mass. If we were to kind of simplify it down even more, the simplest way we could kind of define matter is, it's a little bit slang, but stuff. If it's stuff, it's matter. Anything that has stuff to it, we're talking about matter. It's the stuff of the universe. And just like all the other stuff in our house, in our homes, we can organize, compare, contrast, classify different types of stuff with other stuff. So that's what we're doing with matter. We want to look at comparing and contrasting some different types of matter. And the first way we have of classifying matter is what state of matter are we dealing with? And for right now, we're just going to deal with the three basic states of matter: solids, liquids, and gases. We're not going to get involved in some of the plasmas and some of the strange condensates that can happen at very low temperatures. We're just going to keep it relatively straightforward and work through our different states of matter. Now, in this table, what we're going to go through, the volume and the shape columns are going to be those things that you can observe readily when you're dealing with solids, liquids, and gases. And these are things that we're kind of been made aware of since we were probably pretty young children with how the different states of matter respond to us. What do they look like? What happens with their shapes and their volumes? We're going to go a little bit further than that. The last two columns that you're seeing, the attraction between the particles and the motion of the particles, those are going to be the things that are happening down on the submicroscopic level. You can't directly see them, but what's happening at that level is going to play a big part in what's happening with the volume and the shape, those observable things that you're able to see. So let's start with those observable things. When we look at a solid and we talk about the volume of a solid, we would say that the volume of that solid is definite or fixed. It's unchanging. Basically, it's not going to change based upon normal manipulations. It's already set. That's going to be unchanging. Now, for the shape of a solid, we know solids can come in every imaginable shape. We're not listing shapes. Instead, we want to think about what general properties do we associate with solids and shape. And that general property we can talk about is that solids have a definite or a fixed shape. Your usual manipulations are not going to change that shape of a solid. Think about a key. You can take a key out of your pocket, you can drop a key, you can put a key into a lock. You're not really changing the shape of that key based upon normal manipulation. So we would say it has a fixed or a definite shape. When we go to liquids, the first thing we're going to look at is the volume of a liquid. When we're looking at the volume of a liquid is still fixed or definite. If you have a gallon of water, it's a gallon of water. If you have a quart of milk, it's a quart of milk. Doing different manipulations with that is not going to change that volume. But where liquids start being a little bit different than solids is when we start going to the shape part. When we look at the shape of a liquid, the shape of a liquid is based upon the shape of the container that you're putting that liquid into. And we're familiar with that. Think about pouring water. When you pour water, you can pour it into a tall, skinny vase, or you can pour it into a short, wide bowl. The shape of that liquid is going to change based upon what container you're trying to put it into. When we get to a gas, The volume of a gas is no longer fixed or definite. The volume of a gas is based upon the volume of the container that you're trying to hold that gas into. And we have some experience with that. When you let air out of a balloon, that air you let out of the balloon doesn't stay in that same volume that you had the balloon in. It now spreads out into the new container that you have it in. Same thing's true for the shape. If you're changing volume, you're also changing the shape. When you're letting the air out of a balloon, it has to change shape to get through that skinny neck of the balloon out into that next container. So the volume and the shape are things that we're familiar with. We've been observing these things, these properties of solids, liquids, and gases since we were, small children. Now what we want to do is take a little bit deeper look at that. What is happening down at the particle level that's giving you these observable things? So here now we're dealing with these two right-hand columns of the attraction between the particles and the motion of the particles. And what you're going to see is there's some correlations that happen here. I want to kind of highlight those correlations. The columns that are going to be kind of related to each other, so the attraction between the particles is going to be highly related to what's happening with the volume. And we're going to see that. We're going to see a relationship between those two columns. The other relationship we're going to see is you're going to have a relationship between the shape along with the motion of those particles. We're going to see a relationship there. So we want to go through and we want to talk about this. Because what you're seeing on the right with the attraction between the particles and the motion of the particles dictate what you're seeing macroscopically when you think about these states. So when we look at the attraction between the particles in a solid, I'm calling it very strong. And that very strong attraction between the particles in a solid means they're not going to break away from each other. If they're not able to break away from each other very easily, that's where you're going to get that fixed or that definite volume that we saw initially because of that very strong attraction between the particles. Now, because there's such a strong attraction between these particles, there's very little motion in the particles. The only thing that can happen is that those particles can vibrate in place. So if they can only vibrate in place, they can't move. In order to change shape, you have to be able to have a little bit more motion than just kind of vibrating in place. So that's why, being they can only vibrate in place, you're getting this fixed or this definite shape that you're associating with for solids. Now for a liquid, the attraction between the particles is still pretty strong. Being it's still pretty strong, remember, it's the volume and the attraction between the particles are the columns that are tied together. This strong attraction between the particles is what's going to give you this definite or fixed volume still. But in a liquid, the attraction between the particles is a little bit less than a solid. Remember, in a solid, we said the attraction was very strong. For a liquid, we just said it was strong. What that means is because it's slightly weaker, we get slightly more motion. In a liquid, the particles can move a little bit more than they did in a solid. Solid just vibrate in place, but a liquid, they can slide past each other. If they can slide past each other, you can adapt to new shapes. Even though the volume's still fixed, that little bit of extra motion you can get, you can slide past each other to adjust to a new shape. Now, for a gas, I listed the attraction between the particles as none. That's probably a little bit of an oversimplification. There are attractive forces between the particles in a gas. It's just that they're very weak. They're so much weaker than you see in a liquid or a solid. It's kind of easiest just to imagine there aren't any. So if we don't have any attraction between the particles, there's nothing holding the particles fixed to each other. They can adapt to new volumes. Remember, it's the volume and the attraction between the particles that have a relationship here. There's nothing holding those particles in close proximity to each other. They can adapt to new volumes. Well, there's nothing holding them close to each other. The motion of these particles, you're going to have fast, random, wild motion between these particles. They're just going to be zipping at high speeds in every possible direction. So you're able to get not just the volume of the container changing, the shape of the container also has to change with that. So when you think about what's happening with your states of matter, solids, liquids, and gases, what's happening with the volume and the shape, those things that you can see, is directly impacted by those two things that you can't see, the attraction between the particles and the motion of the particles. So besides classifying by what state that matter is, there's a different classification system we can use. And this is classifying matter based upon composition, meaning what is it made up of. So I'm going to do this in a chart type form as well, but it's going to be a little bit different chart. Instead of just kind of a gridded table, what I want to do is a little bit of a flow chart with you. And I'm going to put matter all the way at the top of this flow chart. And the first way you can break down matter based upon composition, the first splitting point is you can talk about things either being pure substances or mixtures. If it's a pure substance, it's just one thing. If it's a mixture, it's a mixture of more than one thing. And you don't have to overcomplicate this. You can think about this the same way you might describe your pet cat or dog, or someone else's pet dog or cat. That dog is either a purebred dog, meaning there's only one breed that went into making that dog, or your dog is a mixed breed dog. Sometimes we call those mutts. They're a mixture of more than one breed in there. Same thing happens here for matter. That matter is either made up of one thing, making it a pure substance, or it's made up of mixture of more than one thing, giving us that mixture. We can break pure substances and mixtures down to be even more specific. So pure substances we can break down into either being an element or being a compound. So let's start with our elements. Our elements are our most basic building blocks chemically. Yeah, there are technically ways of breaking down, atoms and specific elements, but generally we think about our elements as kind of being our most basic building blocks. And you're familiar with a lot of elements already. Some examples of ones you're familiar with: copper. If you look at a copper pipe, kind of think about your plumbing, not the white plastic PVC pipe, but kind of that orangish brown pipe kind of behind sinks, behind faucets, those type of things. Those are copper pipes. That's the element copper. Another element that we're very familiar with is carbon. It's got the symbol C. So for carbon, when we're thinking about carbon, there's a couple different forms of carbon that we're familiar with. One is if you are writing with a pencil, that graphite that you're writing with is one form of carbon. A different form of carbon, and one that you're also familiar with, is diamond. Diamond jewelry, that diamond is just the element carbon arranged in a very specific way. Pure substances, we can also have compounds. So for this, there's a key part to this definition that we have to make sure we're really fully understanding. Compounds are a chemical union of elements. And I kind of capitalize the union part of that because that's going to be the key part in this definition. A chemical union of elements. That means elements have come together, unified to form one brand new thing. It's not a mixture of elements. Those elements have come together, changed from their original forms, to produce one new thing from that combination. So let's talk about some examples of compounds that you're familiar with. Probably the most familiar one is H2O, water. Water is a good example of a compound. It's not a mixture of elements. If you look at hydrogen and oxygen and oxygen have come together, reacted, unified to form one new thing. This new union does not have any of the old properties of the original elements that were used in its creation. So you don't want to think about water as a mixture of hydrogen and oxygen, because it's definitely not. If you look at hydrogen, hydrogen is a colorless, odorless, explosive gas that's very flammable as well. When you think about hydrogen, think about the Hindenburg, the blimp that had that catastrophe in New Jersey. Oxygen, you're a little bit familiar with oxygen. Oxygen is also a colorless, odorless, highly reactive gas. If you've ever been in a nursing home or a hospital, you've seen the oxygen cylinders and the warning labels on them: danger, explosive, flammable. Or if you've ever driven up on the road and seen these cylinders being carried. Water is not a mixture of those two very reactive, flammable, explosive gases. Water has new properties that resulted. Water is one thing that formed from the union of those elements. Another compound that we're familiar with is NaCl, sodium chloride. You're kind of familiar with this as table salt. So for table salt, what you're looking at for table salt is sodium and chlorine, but it's not a mixture of sodium and chlorine. Sodium is this metallic substance that's a solid, that's very shiny, that reacts violently with water. Meanwhile, the element chlorine is this noxious, choking yellow gas. Think about World War I trench warfare. That sodium chloride is not a mixture of those two very reactive things. It's the union of them. They have come together to form something brand new that doesn't have the same properties as it had the individual pieces. So those are pure substances. Our mixtures can also be broken down into some subcategories. So we have homogeneous mixtures and heterogeneous mixtures. So these are all based upon what does that mixture look like. In a homogeneous mixture, you're going to have things be uniform in appearance. It's going to look like just one thing, even though there are many things in there. So an example of a homogeneous mixture that you're familiar with is most likely the milk in your fridge is a homogeneous mixture. There are thousands of things in your milk. There are sugars, water, protein. Unless it's skim milk, there are some fats and lipids in there. There are vitamins, there are minerals in there. There's tons of things in milk. But when you look at a glass of milk, you can't see the different parts. It's completely uniform in appearance. Another good example of a mixture is salt water. When you have a glass of salt water, it looks like one thing. You can't see the salt from the water. That salt water is completely uniform in appearance. We can also have heterogeneous mixtures. In a heterogeneous mixture, you can see the parts. You can see that there's definitely more than one thing in there. So some examples you're familiar with that would be sand and water. If I have a glass of water and put a teaspoon of sand into that glass of water, you can very clearly see, hey, there's sand, hey, there's water. I can see the different parts. Many of our food items are heterogeneous mixtures. Our classic example would be pizza. When you're looking at a pizza, you can see the different parts. Crust, cheese, sauce, toppings. You can see that there's more than one thing in there. Other examples, things like salads, lettuce, tomato, croutons, cheese. You can see the different parts that are in there. So when you're looking at homogeneous versus heterogeneous mixtures, you really want to just be looking at how do they look? What do those parts actually look like? Are they uniform in appearance? If they're uniform in appearance, you have a homogeneous mixture. You can see different parts, you have a heterogeneous mixture. Key thing is making sure you don't mix up compounds and homogeneous mixtures. The key thing here, and I can't stress this enough, this idea of it not being a mixture. A compound is a union of elements. They've come together to produce something with unique properties. They've chemically combined. They've chemically changed to form one unique thing. Water is one thing. It's not a mixture of hydrogen and oxygen. Kind of one of the last things we want to do when we are looking at matter is talk briefly about chemical versus physical changes, because chemistry is kind of the study of the changes of matter. You could have that as the subtitle of a book. Any chemistry book you look at could really be called chemistry, and then the subtitle being the science of change. And here we're talking about changes in matter, and we have two main types of changes in matter. We can have chemical changes, or we can have physical changes. And the key thing is the composition changing? In a chemical change is going to involve a change in the composition of that material. A new substance is being formed. There's truly a change in composition. And some chemical changes that you're familiar with, burning, oxidation, rusting, tarnishing, you're familiar with these. When you think about burning a piece of paper, that transformation of that burning of that paper is definitely a chemical change. What you are getting out is very, very different than what you started with in terms of that paper. Same thing kind of goes with oxidation. Rusting is actually just a specific type of oxidation. But if you look at a pure piece of iron versus one that has been rusted after some time, that rust on that outer part of the iron is completely chemically different than the iron that you started with. There is a change in composition. So another kind of chemical change that you're familiar with would be tarnishing. You might see this with your silver forks, knives, spoons, or with your silver jewelry. You may notice that after a while, it kind of gets dark. It's not that bright, shiny gray anymore. And there may be a very thin black film coating on it. Well, that thin black coating is tarnish. That tarnish is fundamentally different chemically. It's a different material than the silver that it came from initially. So those are your chemical changes. Physical changes, you do not have a change in the composition of the material. You still have fundamentally the same substance present. It hasn't had a change in composition. Some physical changes that we're familiar with are things like changes of state. We just talked not too long ago about solids, liquids, and gases. So going through those did not change just the actual chemical composition of that. Boiling and freezing are not chemical changes. Those are going to end up being physical changes. When you take water and put it in a pot on the stove to boil, well, you get that water boiling, some of that liquid is going to turn into water vapor, that gas form of water. Well, it's still water, whether it's in a gas form or a liquid form. You didn't change the composition of the material. Same thing happens if you think about making ice cubes. If you put water in a plastic tray and put it in the freezer, as that liquid water turns into solid ice, you just change the state. It's still water, just of a different form. It's now in its solid form instead of its liquid form. So those didn't change the composition of the material in a chemical way, they just changed the state. So changes of state are definitely physical changes. Also, any sort of mechanical changes are going to be physical changes in matter. So things like ripping, tearing, grinding, cutting, any of those are just going to be physical changes. When you take a piece of paper and cut it in half, you still fundamentally have paper. Even if you tear that piece of paper into 300 little bitty pieces and it doesn't function as a textbook page or a document anymore, it's still paper. You haven't changed any of the chemistry, any of the composition that happened there. Now, if you would take that paper and burn it, well, now you're changing it into something brand new. New composition is going to be a chemical change. So anytime you're trying to decide between chemical and physical changes, you just want to look at, was there a change in the composition of the material? If your answer is yes, there was a change in the composition of the material, you're looking at a chemical change. If there was not a change in the composition of the material, then you're just looking at a physical change.